All right, let's get into it. Christopher Nolan's Interstellar. I mean, it's so much more than just a sci-fi movie, isn't it? It's this massive, deep dive into human survival, and it's backed by some seriously mind-bending, real-world science. It really makes you wonder, when we're backed into a corner, where's the line between incredible hope and just plain hubris? This line, it's really the heart of the entire film. It's this bold declaration that, our future is out there in the stars. But at the same time, it hits you with this terrifying question. What if we actually can't leave? Or maybe, what if we shouldn't? So, before we can even think about shooting for the stars, we've got to understand what's pushing us out the door in the first place. The problem on Earth isn't a war, it's not some asteroid, it's something way more fundamental, something biological. The big bad in the movie is this thing called the blight, which is basically a global crop killer. And what you're seeing here is the chillingly plausible science of how it works. It's a vicious cycle, right? First, the blight just starts eating nitrogen right out of the soil. That kills the plants, which means less oxygen in the air. And finally, crops start going extinct. Wheat, okra, you name it. And the whole food chain just collapses. So, let's break down that death spiral. Step 1. The blight attacks our crops, sucking the nitrogen they need right out of the ground. Step 2. As all that plant life dies off, the oxygen levels in our atmosphere just plummet. And step 3, this kicks off a mass extinction of our food. Pretty soon, only the toughest crops like corn are left, and honestly, even they're living on borrowed time. Okay, so Earth is basically on life support. Humanity's at a crossroads. Do we try to fix this dying planet, or do we just bail? And this isn't just a simple what should we do question, it's a massive ethical dilemma. And that whole dilemma is perfectly captured by these two plans. On the left, you've got Plan A. The goal? Save everyone who's alive right now. The idea is to build these huge space stations and lift them off Earth. The problem is, they haven't solved the gravity equation to actually do it. Then on the right, you have Plan B. Save the species. This is the population bomb, a bank of frozen human embryos. The catch? You have to leave every single person on Earth behind to die. So yeah, it's the ultimate choice. What is more important to save? The people or the species? Do you rescue everyone who's alive right now with all their hopes and memories? Or do you sacrifice them all just to make sure the human genetic blueprint survives somewhere out there in the cosmos? And this is where it all gets really murky. Because see, Plan A was probably never going to work. So was the hope it gave to everyone on Earth actually real? Or was it just a noble lie, something to keep society from completely falling apart, while the real mission, Plan B, was secretly underway? It's this brutal kind of utilitarianism, the idea that the death of everyone alive today is a fair price to pay for the long-term survival of the human race. All right, so we know the stakes. We know the impossible choices. Now, let's get to the how. And this is where we leave biology and ethics behind and jump straight into the absolutely staggering physics you'd need to pull this off. To travel across a galaxy, you can't just fly in a straight line. You need a shortcut. And that shortcut is a wormhole, what scientists call an Einstein-Rosen bridge. Think of it like this. Imagine space-time as a big sheet of paper. Instead of crawling all the way from one side to the other, you could just fold the paper in half and punch a pencil straight through. You didn't go faster than light, you just bent the universe to your will. Once they get through that wormhole, the crew runs into a whole new enemy, time itself. On the very first planet they explore, which orbits a giant black hole, this is the exchange rate. For every single hour they spend down there, 7 years pass for everyone and everything they left behind. Just let that sink in. So why that insane time difference? Well, it all comes down to Einstein's theory of general relativity. The gravity from something as massive as the black hole Gargantua doesn't just pull on things. It physically warps and bends the fabric of space-time. And the closer you get to that gravity well, the slower time moves for you. Time literally becomes a physical resource you can spend, and you can lose. Okay, so we've traveled an impossible distance, we've watched time itself become elastic. Now let's look at the destination at the center of it all. The incredible, the terrifying, and the scientifically awesome black hole Gargantua. What you're looking at here is not just some artist's cool idea. It's one of the most scientifically accurate pictures of a black hole ever created. So let's break it down. That super bright, flat ring of light, that's the accretion disk. It's gas and dust heated to millions of degrees swirling around the edge.
The dark spot in the middle is the shadow of the event horizon. That's the point of no return. And that halo of light you see wrapping around the top and bottom, that's a gravitational lens. That's light from stars behind the black hole being bent around it by its own gravity. Wild.
Now, creating this single image took the famous physicist Kip Thorne and a whole team of artists months. They wrote complex computer programs to trace every single beam of light as it bent through curved spacetime. We're talking 800 terabytes of data just to get this right. Now, they did tone down one thing for the movie, the Doppler effect, which would have made one side bright blue and the other deep red. But other than that, the basic physics you're seeing is legit.
And then, just when you think things can't get any weirder, they hit us with the Tesseract. The movie pictures this fifth dimension as a real physical place where time itself becomes a landscape that you can literally walk through. And it turns out the ghost from the beginning of the movie wasn't a ghost at all. It was a gravitational message sent through time. This is all based on a real, though unproven, theory that gravity is the one force that might be able to leak across dimensions.
So, after that epic journey through biology, ethics, and physics that bends your brain, it's time to bring it all back down to Earth. Let's really separate what was solid science, what was a brilliant scientific guess, and what was just, pure movie magic. And this little scorecard here does a great job of laying it all out. In the totally plausible science column, you've got the depiction of the black hole Gargantua, the crazy effects of time dilation, and even the idea of agricultural collapse. Those are all grounded in solid theory. In the middle, you have the speculative stuff. Wormholes, the Tesseract, things that are theoretically possible, but we have zero proof. And then you've got the poetic license. Solid ice clouds, the idea of love as a physical force, and surviving a trip into a singularity. Yeah, that's beautiful storytelling, but it's definitely not science. But when you look past all the cool physics, the movie really pushes us toward one final philosophical question. Do we put all our energy and resources into terraforming a new planet, a planet B, or do we focus on restoring the planet we already have, our planet A? It's the ultimate debate: escape or rebuild? And that really brings us to the most important takeaway from the whole film. For a movie that spends so much time exploring the absolute vastness of space, its core message is surprisingly grounded. The incredible journey to the stars really just serves as one giant, epic reminder of the home we left behind. We can dream of other worlds all we want, but our first and maybe our greatest responsibility is to the one right here, right beneath our feet.